Hello everyone. So in my previous lectures I had discussed the pipelining of first order IIR filters, and in this lecture I am going to discuss the concepts that will be used for pipelining higher order IIR filters. So the concepts that are used are: first is clustered look ahead pipelining technique, and second is scattered look ahead pipelining technique. Okay, so this technique, clustered look ahead pipelining technique, this results in a linear increase in hardware. So linear increase in hardware, and it does not guarantee a stable system. Okay, so during the discussion you will see that the stability is not guaranteed, so it does not guarantee a stable system may or may not be stable, that depends. And the second technique, that is scattered look ahead pipelining, it guarantee a stable system. So starting the discussion with clustered look ahead pipelining technique. Okay, and let's take a nth order IIR filter. So nth order IIR filter of transfer function hz, that is equal to 1 upon 1 minus summation I equal to 1 to n ai z raised to power minus I. Okay, so this is a all pole filter. It is having no zero, it is having all poles. I could have also taken filter like summation I equal to 0 to n minus 1 b of z minus I divided by 1 minus summation I equal to 1 to n ai z of minus I. So this is also a nth order filter. Okay, but I am taking this. All the discussions and derivations are valid for this also. Okay, so again coming back to this filter, so in time domain this can be represented in the form yn is equal to a1 yn minus 1 plus a2 yn minus 2 up to e of n y of n minus n plus xn. So the output is dependent on the present input and the past n samples, starting from minus 1 to minus n, the past n samples. Okay, and the block diagram representation for this is given by xn given to adder, and let's say this is yn, that is multiplied by a1 delayed by 1 clock cycle and given to this. Okay, second adder, this multiplied by a2 delayed by 2 clock cycles and given to this adder. Third adder, so this yn multiplied by a3 and delayed by 3 clock cycle given to this adder. This is nth adder and this is nth branch, that will be multiplied by an delayed by n cycles and given to this. Okay, and this is yn. Okay, so now here you can see that this is having loops. So this is loop number 1, this in blue color is loop number 2, and this one is loop number 3. Okay, and this is the last, that is loop n. So it will have total n loops. Total number of loops that are n, and each loop is associated with a loop bound, so we can calculate very easily. So loop and its loop bound. So for loop number 1, it has two computational unit, one multiplier and one adder. So let Tm and Ta are computation time of adder and multiplier respectively. So total of this computation time is Tm plus Ta. Okay, and it is having n number of adders. So this is loop 1, this is having n number of adders, so this is completing loop 1. Okay, so dot n divided by number of delay element is 1. For loop 2, loop 2 is having one multiplier and n minus 1 adder. So Ta dot n minus 1, and it is having two delay elements, so divided by this. So this nth loop will have one multiplier and only one adder, so Ta, and it is having n delay elements, so divided by n times d. Okay, so comparing the loop bounds, it is evident that loop 1 is having the maximum loop bound, so this is iteration bound. Okay, so T iteration bound is Tm plus Ta dot n divided by 1. Simple reason is that it is having minimum number of delays and maximum number of computational unit in the loop. Okay, so that's why its loop bound is maximum, and this will be the iteration bound for this nth order IIR filter. And so this is critical loop. Critical loop is loop 1. Okay, and one more thing you can see that this filter, in this filter, total number of multipliers are n. Okay, in each branch there is one multiplier, and total adder that are also n. Okay, so for the considered filter, total multiplication operation is n and total add operations are also n. So now if I talk about its sample rate, so that will be limited by this iteration bound, and this is the limit up to which I can reduce the sampling period. Okay, after that it is not possible. So To further increase the sampling rate and to reduce the sampling period, this need to be optimized. And the basic idea of clustered look ahead pipelining is to eliminate this loop. Okay, so if this loop is eliminated from the circuit, so the next loop, that is loop 2, is having a loop bound of Tm plus Ta dot n minus 1 by 2d, that is definitely less than the value of loop 1. Okay, so if I eliminate loop 1 from this circuit, the loop 2 is having much lower, the loop 2 is having a lower loop bound, and from the remaining loops this will be the maximum loop bound value. So this will be the new iteration bound for the updated circuit. Okay, and now the sampling period can be reduced up to this value. Okay, further you want to increase, further eliminate loop 2, so the next loop will be the critical loop for this circuit. So this is the idea, that eliminate the critical loop. Further you want to increase, eliminate next loop. Further you want to increase, eliminate next loop. Okay, so this can be explained in terms of transfer functions. So I have yz by sz, that is equal to 1 upon 1 minus Ez inverse plus E square z minus 2 plus E cube z minus 3 up to e raised to power n z raised to power minus n. So this loop with one delay is associated with this term, power z raised to power minus 1. Okay, so to eliminate this loop from the circuit, we have to eliminate this term from the denominator. So if this term is eliminated, okay, so this loop corresponding to this term that is having only one delay element will be eliminated from the circuit. Okay, so the basic idea is to eliminate loop 1 that is having one delay element that is associated with term z raised to a minus 1. So eliminate the term minus e z raised to power minus 1 from transfer function hz. Okay, so new loop new critical loop will be loop 2, okay, with loop bound Tm plus Ta dot n minus 1 divided by 2d, and that will be the critical loop. Okay, and this will be associated with the term z square, because it is having two delays in time domain is equivalent to z raised to power minus 2 in z domain. Okay, so sampling rate, or you can say sampling period, can be increased can be decreased up to Tm plus Ta n minus 1 by 2d. Okay, and how this can be achieved? By retiming. Simple. By retiming you can replace the delay element at appropriate place, and you can achieve the sampling period equal to this. Okay, further need to optimize, further you want to decrease the sampling period. Okay, so eliminate critical loop, and this time the critical loop is associated with this a square z square. This means eliminate term a2 a square z minus 2. Okay, so this coefficient will be updated because we will perform some multiplication in numerator and denominator, but this power will remain same, z square. Okay, so this process go on. Okay, and we can continue this up to m level. Okay, that means eliminate term z is to power minus 1, z is to power minus 2, up to z is to power minus m. Okay, so after doing this, the critical loop will have a loop bound, and that will be iteration bound of the circuit, some factor in numerator divided by m. Okay, so here you can see that this is having 2 in denominator, this is having n in denominator, this will have m in denominator. So sampling period can be reduced up to this point. Sampling period can be reduced by factor m, by factor m, and this is called m level scattered look ahead pipelining. Okay, so I will take a example to explain the whole process. So consider a filter. So consider a filter represented by transfer function HZ, that is equal to 1 upon 1 minus 5 by 4 Z inverse plus 3 by 8 Z minus 2. That can be also written as 1 minus 1 by 2 Z inverse multiplied by 1 minus 3 by 4 Z minus 1. Okay, so this is a all pole filter having no zeros and poles at 1 by 2 and 3 by 4. In time domain, I can write yn is equal to xn plus 5 by 4 yn minus 1 plus minus 3 by 8 y of n minus 2, and I can draw the block diagram for this following this equation. So xn adder, and this is yn multiplied by 5 by 4 delayed by 1 delay element and given to this adder. We have one more adder. Okay, and this will be multiplied by minus 3 by 8 delayed by 2 delay element and given to this adder. So this is a second order IIR all pole filter with number of adder that is equal to 2 and number of multiplier that is also equal to 2. Okay, and let the computation time is TA and TM. So this is having two loops. This is loop 1 and this is loop 2. So loop and loop bound. So for loop 1, the loop bound is Tm plus 2Ta divided by 1, and for loop 2 the loop bound is Tm plus Ta divided by 2. So obviously this is the critical loop and this value is the iteration bound. This is critical loop and the iteration bound is Tm plus 2Ta by 1. So T sampling for this circuit can be reduced up to this value, okay, by retiming and placing resistors in between. Okay, now suppose I want to increase the sampling rate further. For this, T sampling need to be reduced, and for this first loop should be eliminated. Okay, so this term 5 by 4 Z inverse, this should be eliminated from the transfer function. Okay, so this can be done by, if this is my transfer function Hz given by 1 upon 1 minus 5 by 4 Z inverse plus 3 by 8 Z minus 2. If I multiply and divide the numerator by value 1 plus 5 by 4 Z inverse divided by 1 plus 5 by 4 Z inverse. Okay, so same coefficient with sign, reverse sign. So that will become 1 plus 5 by 4 Z inverse in numerator. So in denominator I will have 1 plus 5 by 4 Z minus 1 minus 5 by 4 Z minus 1 minus 19 by 16 Z minus 2 plus 15 by 32 Z minus 3. This term get cancelled out and I have finally 1 plus 5 by 4 Z minus 1 divided by 1 minus 19 by 16 Z minus 2 plus 15 by 32 Z minus 3. So this is the new transfer function, updated one. And in time domain I can write yn is equal to xn plus 5 by 4 xn minus 1 plus 19 by 16 yn minus 2 minus 15 by 32 y of n minus 3, which can be represented by a block diagram like this. Xn, okay, so it is delayed by 1 multiplied by 5 by 4 and added to itself. Like this, and suppose this is yn, so we have multiplication factor 19 by 16 delayed by 2 delay element and added to this, and this will be added to yn multiplied by minus 15 by 32 delayed by 3 delay element and given back to this adder. So this is FIR part, that is non-recursive, and this is IIR part. So you have already seen that by applying look ahead transformation, the circuit is divided into two parts, FIR and IIR. Okay, so now talking about its loop and loop bound. So it is having two loops similar to the original circuit, two loops in the original circuit and two loops by applying a scattered look ahead transformation. Okay, so loop 1, this is loop 1, let's say this is loop 1, so its loop bound is Tm plus 2Ta divided by 2, and loop 2, it is having loop bound of Tm plus Ta divided by 3. So now this is critical loop, and T iteration bound is Tm plus 2Ta by 2. So this can be pipelined. Now we have additional amount of delays in loop, and this is FIR part, so this can be appropriately pipelined to decrease the sampling period up to this amount. So I am not getting into this, that how the sampling period will be equal to Tm plus 2Ta by 2. This can be easily done by retiming and pipelining the FIR and IR part respectively. Okay, so now further you want to increase the sampling rate. So what you can do, in this filter you can eliminate Z minus 1 as well as Z minus 2. You can eliminate both the terms. Okay, and for this what you have to do, okay, so now what we are doing, we are eliminating, we have H set, our original filter H set, in which Hz was equal to 1 divided by 1 minus 5 by 4 Z minus 1 plus 3 by 8 Z minus 2. Okay, now eliminating Z minus 1 as well as Z minus 2. Okay, so this can be done by multiplying numerator and denominator by factor 1 plus 5 by 4 Z inverse, and by little calculation you can figure it out that to eliminate this term we need to add 19 by 16 Z minus 2. This will be in numerator, and in denominator 1 minus 5 by 4 Z minus 1 plus 3 by 8 Z minus 2 multiply by the same term 1 plus 5 by 4 Z minus 1 plus 19 by 16 Z minus 2. Okay, and the final expression will be 1 plus 5 by 4 Z minus 1 plus 19 by 16 Z minus 2 in numerator divided by 1 minus 65 by 64 Z minus 3 plus 57 by 128 Z minus 4. Okay, so now without drawing I can say that the iteration bound of this circuit will be Ta plus 2Ta by 3, that is associated with this term. Okay, here I have Tm plus 2Ta by 2, and here I have Tm plus 2Ta by 1. So by increasing the level of transformation, okay, this was for m equal to 2, So we will say that it is a two-stage pipeline. Okay, for m equal to 2, the iteration bound reduced by factor 2. Earlier it was Tm plus 2Ta, now it is Tm plus 2Ta by 2. Okay, so for m equal to 3, now for 3-stage pipelining, T infinity is Tm plus 2Ta by 3. Okay, so for m stage pipelining or m stage clustered look ahead transformation, this can be used interchangeably for IIR filter. Okay, so the iteration will be for this filter Tm plus 2Ta by m. Okay, so this can be the possible sampling rate. So T sample can be reduced up to T infinity by appropriately pipelining the FIR part and retiming the IIR part. Okay, so now talking about the hardware increase, hardware complexity. Okay, so original circuit, this is my original circuit. It is having 2 adder and 2 multiplier. Okay, it is not having any FIR or IIR part separate. It is having only one IIR part because it is a all pole filter. So for original circuit, the IIR part is having 2 adder and 2 multiplier because it was a second order filter. For m equal to 1, eliminating the term z equal to minus 1, now the circuit is something like this with the FIR part and IIR part. So this FIR part is having 1 adder and 1 multiplier. It is having 1 adder and 1 multiplier, and in IIR part still 2 multiplier, 2 adder. IIR part it is having 2 adder and 2 multiplier. For m equal to 2, so you can easily say that this IIR part, that is the denominator, it will have it is having 2 terms, so it will have 2 multiplier and 2 adder, 2 add operation, 2 multiply operation. So 2 adder, 2 multiplier, and the FIR part. Okay. Now it is having 2 addition and 2 multiplication. So 2 addition and 2 multiplication. So for value m, any value m level pipelining. Okay, the circuit will have a IR part with 1 adder and 1 multiplier, and FIR part with, okay, and the iteration bound will be, T iteration prime will be T iteration bound of original circuit divided by m. So the sampling rate can be increased up to this factor. So you can see that there is a linear increase in hardware, adder and multiplier increases linearly. Okay, that is by m, by applying m level of pipelining. And this is in FIR part. In IIR part, no change. Okay, so talking about the terms that should be multiplied in numerator and denominator. Okay, so this can be calculated by using a formula. Okay, so given a filter HZ, nth order IIR filter HZ, that is equal to 1 upon 1 minus summation k equal to 1 to n E of k z minus k. So this ak is coefficient. Okay, so now generalizing m stage clustered look ahead pipelining recursive filter can be obtained by multiplying numerator and denominator of the filter transfer function. Okay, so hz should be multiplied and divided by the transfer function given by this formula, that is summation I equal to 0 to m minus 1 r subscript I z of minus I. So what we are doing, we are introducing additional poles and 0. Okay, we are introducing m additional poles and zeros, where Ri is equal to 0 for negative value of I, R0, that is for I equal to 0 it is 1, and for I greater than 0 it is given by summation k equal to 1 to n E of k dot R of I minus k. Okay, so using this formula I will calculate the terms to eliminate z raised to power minus 1 and z raised to power minus 2. So this was the filter that I had taken. So this can be written in the form 1 upon 1 minus is common in bracket 5 by 4 z minus 1 minus 3 by 8 z minus 2, because this term is minus. So it is having two coefficients, a of 1 is plus 5 by 4, a of 2 is minus 3 by 8. So suppose I want to eliminate z of minus 1, so eliminate z of minus 1, that means that m is equal to 2. So the transfer function will be given by summation I equal to 0 2 minus 1 r of I z minus I, and that is equal to r of 0 plus r of 1. 2 minus 1 is 1, z of minus 1. Okay, so r of 0 is equal to 1, r of 0 is 1, and r of I, that is r of 1 in this case, so that is given by summation k equal to 1 to n ak r of I minus k. So k equal to 1 to n e of k r of I minus k, and that is equal to, okay, n is 2 in this case because we have considered a second order filter. So this is a1 r of okay, and I is 1 for this, so 1 minus 1, that is 0. So this is a1 r0. Okay, so this will be equal to a of k, so a1 r of I is 1, so 1 minus k for 1 minus 1 plus a2 r of 1 minus 2. So this is 0 because for negative values r is 0, and this is a1 r0, and that is equal to 5 by 4, r0 is 1, Okay, so R1 is calculated. So the transfer function is putting this value into this equation, R0 and R1 into this equation. I have 1 plus 5 by 4 z minus 1, and this was the term that I had multiplied in numerator and denominator. Okay, now eliminating z minus 1 and z minus 2. So for this, m will be equal to 3. So I have to multiply and divide the numerator by function summation I equal to 0 to m minus 1, that is 2 r of I z of minus I, and r0 is 1 and ri is given by summation k equal to 1 to n is again 2, second order filter, e of k r of I minus k. So this will be r0 plus r1 z minus 1 plus r2 z minus 2. So r0 is 1. Okay, by this formula we will calculate r1 and r2. So r1 is summation k equal to 1 to 2 e of k r of 1 minus k, that is a1 r0. Okay, that's it. Next term will be negative, so that will be 0, and this is 5 by 4 into 1, and r2, that is summation k equal to 1 to 2 e of k r of I minus k. So I is 2 minus k, that is equal to a of 1 r of 1 for k equal to 1, 2 minus 1 is 1, plus e of 2 r of 0. Okay, and this is e of 1 is 5 by 4 and r of 1 is also 5 by 4, and a of 2 is minus 3 by 8, and r0 is 1, and this is 19 by 16. So putting the value of r0, r1 and r2 in this expression, we have 1 plus 5 by 4 z minus 1 plus 19 by 16 z minus 2. Okay, so this is how we can calculate the expression that need to be multiply and divide to numerator and denominator.